All right, this question reads, a diffraction grating with 500 lines per millimeter is used to observe diffraction of monochromatic light of wavelength 600 nanometers. The light is passed through a narrow slit and the grating is placed so that its lines are parallel to the slit. Light passes through the slit and then the grating. An observer views the slit through the grating at different angles, moving his head from X parallel to the grating through Y opposite the slit to Z parallel to the grating on the opposite side. How many images of the slit does he see? So this is obviously a diffraction grating type problem. And so the first equation that should come to mind is d sine theta equals n lambda. This is a question where we need to solve for n based on maximizing the diffraction that can occur here, right? So we're just solving for how many order numbers sort of are there here. They don't tell us the distance between each slit in our diffraction grating, like the distance between each one of these. They just tell us that there's 500 lines per millimeter. So usually we'll call that capital N, 500 lines per millimeter, which means that 1 over n solves for d, the thing we need to know for our equation. So we have 1 divided by 500 lines per millimeter, right? So when we solve this 1 over 500, keep in mind that it's still in millimeters. So 1 divided by 500 means that there is 0.002 millimeters between each slit in the diffraction grating, right? Because if there's 0.002 millimeters times 500, right? There's our 1 millimeter. So there's 500 lines per millimeter. So there's 0.002 millimeters is the distance between each one. So we could change milli to 10 to the negative 3. I could rewrite this 0.002 times 10 to the 3, 2 by 10 to the negative 1, 2, 3, 4, 5, 6, right? Because this is 10 to the negative 3, 10 to the negative 3. So we got 2 by 10 to the negative 6 meters. That's how much distance is in between each slit and the diffraction grating. Pretty small number. Remember that we're solving for n when theta is as big as it could possibly be, 90 degrees. So we're always solving for the diffraction angle, theta, sort of relative to the 0 order. Where the eyeball is now, you could say, well, there's going to be a 0 order there. Note that we could not get an angle greater than 90 degrees, right? So that's sort of the maximum value. Sine 90 is the sort of limit that term can reach, right? So we're going to use 90 degrees for theta. It tells us that the wavelength was 600 nanometers, right? So we're given that sort of up here, 600 nanometers wavelength. So let's rewrite lambda as 600 nanometers, right? With 10 to the negative 9 for nano, which is the same thing as 6 by 10 to the negative 7 meters, right? So 600 by 10 to the negative 9 is 6 by 10 to the negative 7. That's the wavelength. And I think we're good to solve for n now. So n would be equal to, if we just sort of divide by lambda, we have d sine theta over lambda. Sine 90 is 1, right? So that term just sort of goes away, and we get 6 by 10 to the negative 7 meters for d, divided by, 2 by 10 to the negative 6, that was the denominator. 6 by 10 to the negative 7 meters was the wavelength, lambda, in the denominator. The numerator was this 2 by 10 to the negative 6 meters. And so note that the order number n is going to have no units. These units meters cancel. So I've got my 2 by 10 raised to the negative 6 divided by, open parentheses, 6 times 10 to the 7 equals, you get n equals 3.3 repeating. Okay. And so the first thing that comes to mind is, oh, we can't have a third of an order number, right? So we'd see like there's an order right here, there's 1, there's 2, there's 3, but we can't 0.33. So you round it down. But then don't be so quick to say, oh, n equals 3. A is correct. That's not how many images this creepy eyeball floating off to the right will see. It will see 1, 2, 3 images down here. It will see an equal 1, 2, 3 images above the zero order, and it sees the zero order itself. And so what I was mentioning is that when you have a problem that's like this, that requires you to solve for n in order to ultimately deduce how many images, how many, sort of bright spots will be seen in a diffraction grating, you always have to double n and then add 1, right? You always have to double n to account for the other order on the other side of the zero order, and you have to add in the zero order itself. And so you round it down to 3, and then say, oh, we got to double it to account for the other side. So that's 6 plus 1 is 7. So the correct answer to this question is D, 7, right? Because you're going to see 3 order down here, 3 order up here, plus the zero order. 3, 6, 7, 8, 9. Whoops. 3, 4, 5, 6, 7 is how you count, actually. You count like that. 7.